All right, well, welcome everyone. Thanks for coming out. Really appreciate it. I promise I'm going to make it worth your while, and we'll get done in time for fireworks, I think. So you'll still have a chance to see those. Probably most of you know me, but in case you don't, my name is Brian Jackson. I'm a professor here in the physics department, and I'm an astronomer. I'm the speaker for tonight. So we usually do a short introduction for the speaker. So I'll do a little introduction for myself as well. But you're here at First Friday Astronomy. These are a monthly lecture series. They take place on the first Friday of every month, 7:30 p.m. We're going to be in this room, I think, through the fall. The building we're usually in is under repairs this coming fall, so we're actually going to be here for the rest of the calendar year. These events are also online, so you can live stream us. I think if you Google Boise State Astronomy on YouTube, it'll show up if you search our name. So you can find our live stream, which should be running right now. We do these every month. We have a great lineup of speakers for the next several months. We have almost all the speakers lined up for the fall as well. And as a special treat this coming fall, in September, we are going to plant a moon tree. NASA has a program going back to actually Apollo where they fly tree seeds around the moon and bring them back to Earth and then grow seedlings out of them. And then those seedlings are distributed to educational institutions around the United States. We applied for this like 2 years ago and didn't hear anything back. So I thought, oh, well, we're just not going to get one. But then a few months ago, we finally heard back and they've granted us a moon tree. It's actually on campus now in the arborist's office. And so we're going to plant that at a special event in September for our first Friday in September. As an added bonus, our faculty astronaut, Dr. Steve Swanson, will be our guest speaker for that evening. And so the plan for the September 1st Friday Astronomy, we're going to have a nice talk from Dr. Swanson, and then we're going to go out into the plaza here and plant a tree that flew around the moon. So that should be a lot of fun. So please join us in September for that. But in addition to that, we've got a lot of other great talks coming up in the next semester. This program is entirely donor supported. I think you probably all know this. We rely on your donations to pay for speakers to come in to Boise to stay. We oftentimes pay for we pay for dinner for our students as well. I'm not taking any pay tonight, so you're saving a little money there. But if this is the kind of program you enjoy, please do consider donating. There's information out on the table for how to donate. And then we also have a new semesterly newsletter. It goes out every 4 months, and you can sign up for that at the front table as well. So our guest speaker for tonight is Professor Brian Jackson. Professor Jackson got a bachelor's degree in physics from Georgia Tech in Atlanta, and then went to the University of Arizona in Tucson to study planetary science. We got a PhD in planetary science. He then went to the NASA Goddard Space Flight Center in Washington, D.C., where he's a postdoc for 2.5 years, 2 years and 9 months, before moving to the Carnegie Institution of Washington in downtown Washington, D.C., where he was a postdoc until 2014 and then joined the Boise State faculty in July 2014. So I will be here 11 years, I think today, actually. I came to Boise today, back in 2014. So it's 11 years today for me. Yeah, thanks. Let's see, let me get some lights here. I've put together what I think will be an interesting talk for you. I hope will be an interesting talk for you this evening. Let's see, do you like that better? Or this is better? Okay. This is actually a new talk. A lot of times when you give talks like this, you're kind of recycling old talks. This is a brand new talk, so hopefully you enjoy it. I thought it would be a really interesting to talk a little bit about the history of federal funding of scientific research in the United States. And so this talk is going to be a little bit about that history, but also I'm going to tell you how the sausage is made. I'm going to show you how federally funded scientists develop funding programs with the government. So we're going to look at a NASA proposal. I'm going to show you an evaluation letter that we received on a real proposal, so you can see all the good and the bad news that we get from NASA when we put one of these proposals in, and then talk about prospects for future federal funding of science. This presentation is live on my website. I'm actually giving it from the website right now. So you can visit astrojack.com/endlessfrontier, or you can zap that QR code. It'll take you to the website and you can see the presentation there. If you see any fun videos or pictures you want to follow up on, that's the place to go. So our story begins in January 6, 1939, when two German scientists, Otto Hahn and Fritz Strassmann, published a result that was kind of surprising and a little bit confusing initially. They claimed to have disintegrated uranium atoms. Initially, it wasn't clear what that meant or what exactly had happened. This is the original Nature article, published again in 1939 February, where they report their experiments. And so, as I said, it wasn't initially understood the import of this or even what exactly had happened. This is the first experiments for fission of uranium. Hadn't been done before. Some American scientists and European scientists, other European scientists, followed up on this and were able to produce the same result. So they found indeed that you could cause uranium atoms to split apart. Now, it had been believed something like that was possible, but it wasn't entirely clear how it worked. It sort of violates some basic premises of chemistry, but chemistry that didn't accommodate nuclear reactions. And so this report was kind of a big deal when it came out. The Hungarian physicist Leo Szilard realized that this kind of reaction, neutron-driven fission of heavy atoms, could be used to generate a nuclear chain reaction. In essence, you could cause some atoms to split apart, and the splitting apart of those atoms could cause other atoms nearby to split apart, which could cause more atoms to split apart, and it would result in the release of an enormous amount of energy. Szilard realized, in fact, that you could make a bomb this way. An enormous, powerful bomb, more powerful than anyone had ever made before. And the fact that these first results were reported by German scientists in 1939 was very concerning to him. Szilard basically cast about to find some way to respond to this. I'm not sure why this has gone blank. That's interesting. And he approached Ed Wigner, who was another scientist, and they realized that they probably needed to let the president know about this. The president at the time was Franklin Delano Roosevelt. And so they weren't sure that they could actually get his attention, so they went to the most famous scientist they could think of at the time, Albert Einstein. They drove out to Long Island, where Albert Einstein was sort of vacationing, and approached him with this and explained their concern. These experiments by German scientists could result in the creation of a large bomb. And Einstein reportedly replied, "Wow, I didn't even think of that." So Einstein was not actually a nuclear physicist. You know, of course, he understood the rudiments of the science, but it was not something he had himself studied. So it had occurred to him that this could be a really dangerous situation, that the Nazis could build a bomb. And so Szilard and Wigner worked together with Einstein to draft a letter that was eventually put into the hands of FDR. You're supposed to be seeing the letter right here. I'm not sure why the screen is blank, but I'll show you some excerpts from the letter. These are the key excerpts. Top, the United States has only very poor ores of uranium in moderate quantities. So the US at the time didn't probably have the materials to make a uranium bomb. There are some good ores in Canada and the former Czechoslovakia. It was, of course, former Czechoslovakia because Germany had taken it over. While the most important source of uranium is in the Belgian Congo. And Einstein went on to say, "I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines, which she has taken over. That she should have taken such early action might perhaps be understood on the ground that the son of the German Undersecretary of State, von Weizsäcker, is attached to the Kaiser Wilhelm Institute in Berlin, where the experiments have been conducted, and where some of the American work on uranium is now being repeated." So they were really worried that the Nazis were going to build an atomic bomb. Now, we know, of course, in the aftermath of World War II, that the Germans were actually in the process of building a nuclear bomb. This letter prompted FDR to convene basically a series of panels and institute a program to develop the American nuclear bomb, which you probably are familiar with, the Manhattan Project. And it was this letter that really did that. FDR, along with the rest of his administration, created the Office of Scientific Research and Development within the federal government to lead the effort to create this bomb. It was formally created by an executive order in June of 1941. And so from 1942 to 1946, this project was directed by Major General Leslie Groves. Probably many of you have seen the Oppenheimer movie. This is one of the characters that features very prominently. Of course, nuclear physicist Robert Oppenheimer was the director of one of the major labs that designed the bombs. So, of course, this was a huge deal. And this is the kind of start of our modern funding of federal scientific research. So I think one of the Manhattan Project is a fascinating study of history. But one aspect I think that's often not considered is how much did it cost? How much were they spending for this project? And so this is a chart I found which shows the monthly expenditure on the Manhattan Project here in the yellow bars. And you can see the number of personnel hired in the different colored curves. So the number of construction personnel peaked early because, of course, they had to build all the facilities. Operations and research personnel, the scientists, that came in a little bit later once they could occupy the buildings. The gray curve shows you the total number of personnel. Altogether, the Manhattan Project employed about 130,000 people at its peak. So that's a lot of people. And cost about $2 billion in that day's money. That's about $27 billion in 2023 dollars. So you can see this is an enormous peak here in about 44. Around that same time, total federal spending in 1945 amounted to about $92 billion that year. Of course, this is in the middle of the war, so there's a lot of money being spent. But the cost of the Manhattan Project in those same dollars was $2 billion. And so you can see right off the bat, this is, $2 billion is not a trivial amount of money in 1945, but on the scale of federal outlays that year was not very much. A little bit, about 2% of the federal budget at that time was given over to this Manhattan Project. So the bomb was, of course, built. There was a series of successful tests, and the American military was gearing up to deploy the bomb. The Germans surrendered in 1945, May of 1945. And so the Americans did not actually drop a bomb on Germany. It turns out that the German nuclear bomb project was not all that far along. We didn't, of course, know at the time how far along they had gotten, but they weren't actually that far along. They weren't even to the point of actually having a sort of working prototype. And it's not entirely clear why. One of the folks involved with the German effort was, of course, was Heisenberg, famous physicist. Heisenberg, one of the leaders in the German scientific establishment, was a theorist, not an experimentalist. And so I have heard it speculated that his sort of familiarity with theory didn't translate very well to experiment. He didn't have a good way of sort of translating his sort of chalkboard calculations into experiments and prototypes. I have even heard it suggested that Heisenberg was sort of secretly putting the brakes on the German project to kind of keep them from getting a bomb. I don't know how well established that idea is, but I've heard that suggested. So the Germans were actually not that close to getting a bomb. It turns out this was probably not, at least it wasn't as big a threat as Einstein had worried it had been. And Einstein actually later, when it was discovered how little progress the Germans had made toward the bomb, Einstein later said, I wished I'd never sent that letter to FDR, because this was the beginning of the nuclear age, of course. So the Germans surrendered in May of 1945, but the Japanese were still at war with the United States. And so in August of 1945, the American military dropped two different bombs on Japan, and Japan shortly thereafter surrendered. In fact, one of the reasons that Japan took about a week to surrender after the second bomb was dropped. And one of the reasons that they took so long to surrender was traditionally the American military, when they would demand surrender of an enemy, they would demand unconditional surrender, right? This kind of went back to the Civil War when Ulysses S. Grant sort of demanded unconditional surrender. Well, all surrender has conditions attached, right? I mean, there's not infinite surrender. And so, but the Japanese, when they got this ultimatum from the United States, worried that unconditional surrender meant they would also have to surrender the person of the emperor. And in Japanese culture at the time, the emperor was a sacred and divine being. So they couldn't imagine surrendering the person of the emperor. So it actually was some delay in surrendering to the Americans, partly because they didn't want to give up the emperor. But in the end, the Japanese did surrender. So this is just a sort of a brief thumbnail sketch. I am by no means an expert of the Manhattan Project, But as I said, Manhattan Project was really the beginning of the modern era of federal research and development support. But it was by no means the first example of federal support of research. I think you could argue that the first support at the federal level for research in the United States goes back nearly to the founding of the nation, back to 1803, when Thomas Jefferson, the third president of the United States, purchased the Louisiana Territory from the French emperor. There was a lot of interesting machinations and maneuvering that took place that led to the purchase of this territory. Jefferson himself was troubled by the idea that the American president could actually purchase this big territory. He wasn't sure about the constitutionality of this purchase. He sort of overcame his qualms in part because the French were desperate to sell the territory. Jefferson was worried about foreign powers interfering with the United States, and this gave them an enormous buffer zone against other Spanish territories and British territories up further to the northwest. The price was right too. They paid $15 million for the Louisiana Territory. Now, the purchase was made as a result of negotiations that were initiated by the Americans with the French government with the goal of purchasing New Orleans to control the mouth of the Mississippi. So they wanted to purchase New Orleans from the French government for $10 million. And the French came back and said, well, how about all of Louisiana for $15 million? This works out, the calculation suggests that this works out to about 3 cents an acre. That's a really good deal. So even Jefferson couldn't pass up such a bargain. So he purchased the territory in April of 1803, and very shortly thereafter began to make arrangements to send federally funded scientists out to the territory to survey and explore. This was a part of the continent that had not been well explored by Europeans. Of course, there were lots of other people already living there, but Europeans hadn't done too much exploring, at least not in a systematic way. And so this is a story I'm sure many of you know. Jefferson recruited 2 explorers, William Clark and Meriwether Lewis, pictured here, to lead an expedition, the Corps of Discovery, through the Louisiana Territory, up to the northwestern corner of North America. Jefferson picked Lewis. Lewis was actually kind of a protege of Jefferson's. He was kind of a polymath or a young man who was kind of interested in following in Jefferson's footsteps. And Jefferson sent Lewis kind of all around the eastern seaboard to meet with various scientists and physicians to learn some of the important scientific skills that he would need to conduct this survey. So for instance, Jefferson sent Lewis up to Philadelphia to learn medicinal cures under Dr. Benjamin Rush, who was kind of the premier Revolutionary era doctor of the time. He visited with Andrew Ellicott to learn the use of astronomical instrumentation and learned about preservation of specimens, scientific specimens from Benjamin Smith Barton. The Corps of Discovery departed from the western part of the United States, Illinois, in 1804, and kind of made their way up to the Fort Clatsop in the winter of 1805. They wintered there over that winter and then came back the following year, arriving back in the world civilization in 1806. We actually have a pretty precise map of the journey of the Corps of Discovery across the Louisiana Territory for this expedition, in part because of Lewis's visit to Benjamin Rush. Benjamin Rush, as I said, was kind of the premier physician for the United States at the time, and he had invented a variety of cures, including something he called Rush's bilious pills, and they were colloquially referred to as Rush's thunderbolts. They were a solution of mercurous chloride, and they were a purgative. Anyone know what a purgative is? It's a very strong laxative. And because they contained mercury, at each of the camp stops where this purgative was employed, there was a strong signature of mercury left behind. And so archaeologists who want to trace the path that Meriwether Lewis and William Clark took across the United States are able to trace it as a result of these mercury deposits. So this was, of course, a really important exploration for the early United States, 1803, as I said. Congress appropriated a little over $2,000 for supplies and food for the Corps of Discovery, but that was just the initial appropriation. Along the way, they had to commandeer and purchase various supplies and tools and things. Estimates after the return put the actual cost of the expedition at about $40,000. So this is in 1806 dollars. That year, you can see federal spending amounted to only about $10 million. And again, this is in those days dollars. So the Corps of Discovery cost some teeny fraction of federal outlays that year. This is a recurring thing you're going to see throughout this talk, is that this sort of federal expenditure on research and development has led to these enormous advances in our understanding of the natural world, but they cost a teeny fraction of the federal budget, and this is no exception, even one of the very first federal expenditures for research. But I think you can argue there was an even earlier expenditure on behalf of the American nation, made even before the nation existed. You may know that the Revolutionary War began in April 1775. Depending on exactly what you use as the definition, you could point to the Battle of Lexington and Concord as the first, the initiation of hostilities. That happened in April of 1775. That initiated the Revolutionary War. Of course, a variety of things happened. We're not going to be able to go through all of them, but one of the most famous episodes in the war was the encampment of George Washington and the Revolutionary Army at Valley Forge. The Valley Forge encampment took place between December of 1777 and June of 78. It was a third of 8 winter encampments for Washington and the Continental Army that year. This is an artist's conception of what it looked like. It's a big camp with a bunch of wooden huts that the soldiers built. They built them there. I mean, they didn't, bring materials out there to build. They had to cut down trees and plane boards and things like that to build these huts there in Valley Forge. This is a reproduction of what one of those huts probably looked like. General Washington's orders dictated that the huts should measure 14 by 16 feet, include a fireplace, and be lined with 18 inches of clay for insulation. And you can see the clay between the wooden logs. One of the biggest challenges they had in building these was a lack of sawmills. They didn't have saws to plane the boards, and so a lot of the delay in construction just was the result of soldiers sitting around waiting for one of the other soldiers to finish using the saw so they could use it to plane their own boards. And so, in fact, Washington wanted to contrive a better way of building these huts. He offered a $100 bounty to any person who could provide a suitable alternative to the plan that was being used at the time. So I think you could argue that this was probably the first expenditure on behalf of the American nation for research and development. And to give you a sense for that, the budget, of course, the nation didn't exist at the time. There were no federal outlays. One of the things that Washington was very meticulous about during his service in the Revolutionary War, he declined to take a salary. So he wasn't paid by the government, but he asked that the government reimburse his expenses. And so this is a page from his notes, actually from his aide's notes, of the various expenditures that he made and in fact, this is for July 4th, 1776. On this day in 1776, George Washington purchased a broom, mutton, veal, beef, cabbage, beets, beans, potatoes, and a lobster. After the war, George Washington turned over his meticulous records to the Congress and requested a reimbursement of about $160,000 for 8 years of service during the war. So if we think of this $100 bounty for the development of a new hut as a research and development expenditure, we're talking about $100 out of $160,000 for Washington's expenses. So 0.06% of the expenses that Washington incurred during the war. So again, a tiny fraction. Our current regime of federal science funding dates back to the post-World War II epic. and really originated as a result of a report written by this fellow. This is Dr. Vannevar Bush. Dr. Bush served in several capacities in various science advisory roles, in both the Roosevelt and the Truman White House. He was born, I just think this is really fascinating. Vannevar Bush was born in 1890 and died in 1974. So he was born in the last decade of Queen Victoria's rule. If he were born in Britain, he would have been a Victorian. And he died in 1974 while Nixon was president. So you can that's just an enormous lifespan, you can imagine. Franklin Delano Roosevelt, of course, initiated an enormous program of wartime research, but he saw the benefit to American industry of this federal funding of research. So he wondered whether that kind of funding could continue and what the benefits would be. And so this is the letter that he sent to Vannevar Bush. This is kind of an eye test. You don't have to try to read the whole thing. Basically asking him to explore this question: what would be the benefits of peacetime funding of research and development? And I think one of the key lines here is from FDR's letter: there is, however, no reason why the lessons to be found in this experiment, meaning the wartime research and development funding, while the lessons found in this experiment cannot be profitably employed in times of peace. So Vannevar Bush called together several different committees of scientists and engineers, medicine, natural history, various things like that, to devise a way that we could develop a federal program of research and development funding. What would be the benefits? And he summarized all the results from those committees in a report that he called The Endless Frontier. This report is available online, and it is surprisingly readable. It's only about 40 pages. I read it to prepare for this talk, and I was really impressed not only by how readable it is, but how forward-thinking it was. So I've got kind of two quotes here that I think really struck me from this report. He says at the top, "The most important ways in which the government can promote industrial research are to increase the flow of new scientific knowledge, to support of basic research, and to aid in the development of scientific talent." This report focused a lot not on the sort of big picture benefits to humankind of exploring the natural world. That, of course, features. But a lot of this program of federal support for research and development was cast in terms of economic benefits to the nation. They were really interested in finding jobs for all these GIs who were returning from the war. And Dr. Bush made the argument that the development of new technologies and approaches was going to be very important for developing new industries that could employ all these Americans who suddenly weren't in the military anymore. And one of the key elements of the program that he pitched to the federal government was the idea of developing educational infrastructure to train up all these Americans. And you can see in the bottom here, the committee advising him on this issue held that the opportunity for education and research be provided to all, quote, "that there be no ceilings other than ability itself to intellectual ambition. Every boy and girl shall know that if he shows that he has what it takes, the sky is the limit." And this is in the report, verbatim. To me, that's really amazing to think that someone basically back in the 50s, they were writing this and advocating for this really broad-based development of research. So in 1950, Harry S. Truman signed Public Law 507, creating the National Science Foundation, which provided for a National Science Board of 24 part-time members. This is the creation of the National Science Foundation, this report. Of course, the NSF is not the only agency at the federal level that supports research and development. You're probably familiar with another one, NASA. NASA was created kind of in response to the Soviet space program. The Soviets were having an enormous amount of success launching rockets and eventually, of course, launching Sputnik into space in orbit around the Earth. That terrified a lot of Americans, particularly those in the government. And we created NASA in part as a response to that. NASA was created in 1958. And accelerated work on human and robotic spaceflight is, of course, nowadays responsible for these enormous scientific and technological achievements that have widespread impacts on our nation and the world. I don't think I need to probably convince folks in this room of the benefits of NASA science. And so I'm not going to talk about a lot of the economic developments that come from research and development. I'm instead going to tell you a little bit about how federal funding of research actually works, like I say, at the granular level, how the sausage is made. Oh my gosh, my video's not going to play. Let's see. Oh, there we go. Okay. The U.S.'s response to the Soviet Sputnik satellite was the launch of the Explorer-1 satellite, which was the U.S.'s first satellite to orbit the Earth. The Explorer-1 carried a limited suite of instruments, but it was the first spacecraft to detect the Van Allen radiation belts, which is a cloud of high-energy particles trapped in the Earth's magnetic field. Nobody knew it was there until we flew this spacecraft. Let's see if this will play. So that was the first American satellite in orbit around the Earth. Interestingly, James Van Allen was a professor at the University of Iowa. University of Iowa still has a really robust and kind of famous program in space weather, the sort of study of high energy particles in space. The discovery of the Van Allen radiation belts led to kind of a renaissance, not even a renaissance, a birth of space weather as a field of study. And James Van Allen became a celebrity in that field. I haven't seen this myself, but I have been told that whenever he would show up to a scientific conference, the students would try to steal his belt so they could claim they had Van Allen's belt. This is of course, a much more recent development. You're seeing here a picture of the Rubin Observatory in Chile. The Rubin Observatory is funded by the NSF, the Department of Energy, and a variety of other public and private agencies. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is this enormous observatory in Chile. Construction on the mirror began in 2007, and site construction began in 2015. It just began publishing its first light images in June of this year. This observatory is quite large. You might not be able to tell the scale here. The mirror inside the telescope for this observatory is 8 meters across. So it's huge. It's huge. I'll talk a little more about this observatory later in the talk, but this observatory is going to revolutionize astronomy in some of the same ways that the Hubble Space Telescope revolutionized astronomy. It has a variety of novel capabilities for a ground-based telescope. And so we're going to learn a lot about the solar system, the universe, the galaxy, using this telescope. It's named after Vera Rubin, and I'll show you a short video about why it's named after her. I'll come back to this, but Vera Rubin is a very famous astronomer. She died in 2016, but she made a variety of enormous contributions to our understanding of the universe. In particular, provided some of the key evidence for the existence of dark matter, which we now know makes up most of the matter in the universe. Didn't even know it existed. So how does government funding of science work nowadays? How do scientists develop ideas that turn into federal funding? And how is the money actually made available for research? What do scientists do with the money once they get it? And how does all of this kind of piece together and tie back to Vannevar Bush's vision for this kind of widespread involvement in research? There are a lot of programs at the federal level to support research in astronomy and technology development, engineering. I am, of course, most familiar with space science funding, so I'm going to talk to you today about how NASA funding works, but most of the federal funding kind of works more or less the same way. There's a little bit of difference from one program to the next, but more or less it's very similar. So how does space science research get funded? There's kind of 4 steps. First, you got to have an idea for a science project. You got to find a federal grant program to propose to. You got to write and submit that proposal, and then there's an element of crossing your fingers. Okay, so let's talk about each of these in turn. First thing, of course, is you have to have a good idea for a science project. How do you develop ideas for science projects? Well, some folks are really good at developing ideas for science projects. This is a picture of one of the most famous mathematicians, Ramanujan. Ramanujan was an Indian mathematician born in 1887, died in 1920. He's often regarded as one of the greatest mathematicians of all time, though he had no formal training in pure mathematics. He was born to a relatively poor family in India and didn't really have access to a lot of the professional training that mathematicians had at the time, although he did manage to learn quite a lot on his own. He spent many years basically developing new results, completely novel, proving things that the mathematicians had not been able to prove before, but he couldn't get any attention from the professional mathematics community. He was basically sending letters out all the time trying to get professional mathematicians to pay attention to his work. Here, for example, is one of the most famous formulae that he developed. This is a formula for pi. Probably most of you are familiar with pi. It's the ratio of a circle's circumference to its diameter. It turns out that if you add up a bunch of numbers over here and multiply them together in this very kind of convoluted way, you get an expression that approximates pi very, very precisely. I have no idea how someone would come up with an idea like that. How did Ramanujan come up with ideas like this? All of his formulae look like this, by the way. They're always really convoluted, complex. How does he come up with something like this? Well, he told G.H. Hardy, who was a Cambridge mathematician at the time and a partner of his, how he came up with these ideas. He said, quote, "While asleep, I had an unusual experience. It was a red screen formed by flowing blood, as it were. I was observing it. Suddenly, a hand began to write on the screen. I became all attention. That hand wrote a number of results in elliptic intervals, and they stuck in my mind. As soon as I woke up, I committed them to writing." Ramanujan believed that the goddess Namagiri would visit him in his sleep and would present these equations to him, and then he would just write them down upon awakening. Well, that's one way you can get an idea for a science project. That's not how I usually get ideas for science projects. A lot of space scientists consult the book. This book. This is the report from the National Academies of Sciences, Engineering, and Medicine. The federal government contracts with the National Academies to provide a variety of different kinds of reports, very similar to Vannevar Bush's report from the 50s, providing some insight, big picture ideas for how to guide federal research and development. And in this case, we're looking at the report that some very preeminent space scientists put together, Origins, Worlds, and Life, outlining a program of research in planetary science and astrobiology for the next decade. This is referred to oftentimes in the field as the decadal, because it comes out every 10 years. And it maps out these key science questions that scientists can explore as part of their research program. You're not required to adhere to the ideas in this book. There's no question. You're allowed to suggest other ideas, but it helps if you can point to this book and say, my idea has roots in this book. So the report comes, it's a relatively lengthy report, but a lot of the report consists of these sort of key questions. So here's a table of key questions that we might point to for our research program. And one of the key questions we might be interested in is, what establishes the properties and dynamics of atmospheres and governs atmosphere-surface interactions for planets? Okay. So how do planets' atmospheres evolve over time, and how do those atmospheres interact with the surface of the world? Well, our research group actually studies Mars, and we think a lot about how the Martian atmosphere interacts with the Martian surface. And one of the most interesting, complicated, and poorly understood processes that are involved in those interactions is dust devils. How many of you have seen a dust devil before? Yeah, they happen a lot out in dry regions on the Earth. Well, Mars is very dry and dusty, and so dust devils occur actually all over the surface of Mars. This is a series of images collected by one of the rovers on the surface of Mars, showing you a dust devil on Mars skittering along the surface. So dust devils occur a lot on the surface of Mars. They lift dust from the surface and eject it high into the atmosphere. When the dust gets into the atmosphere, it affects the weather on Mars in some really big ways we don't completely understand. But dust devils play a key role in that meteorological cycle and probably in the long-term evolution of the Martian climate as well. But we don't understand how dust devils work. We can't predict when they're going to occur. We don't even know how much dust a particular dust devil lifts up. But because they have this really profound impact on Martian climate, we really would like to understand them. And so our research group has spent a lot of time actually thinking about dust devils on Mars and on the Earth, trying to understand them. We've been fairly fortunate to have a lot of instruments on the surface of Mars that can actually directly study dust devils. So this is a schematic showing the Mars 2020 Perseverance rover and all the instruments that it includes, including a weather station, the Mars Environmental Dynamics Analysis. Oh, I'm sorry, I should have made sure to look up META. META is the name of the instrument suite. META includes wind sensors, temperature sensors, pressure, and it can also measure dust. And so it's an ideal instrument for studying things that lift up dust, like dust devils. In fact, Mars 2020 personally encountered a dust devil back in 2021. This is a video showing a dust devil actually blowing over the Mars 2020 rover in that year. So here on the top, you're going to see a series of still images as the dust devil approaches the rover. This is a processed version of that image showing you the dust being lifted by the dust devil. And then in the bottom here, you're going to see the atmospheric pressure sensor. And there's actually a microphone on board Mars 2020, which can hear sounds on Mars. So this is what a dust devil striking Mars 2020 looks like. So it's a little sedate, but that's because it's a series of images. Actually, imaging these dust devils passing over the rover is really hard to do, and they got really lucky. They basically were just snapping a lot of photos and hoping a dust devil would pass by. They didn't know that it would. They got lucky and actually caught this dust devil blowing over. I'll play that again for you because I just think it's really fun. You can listen for the little snap at the end of the encounter. Snap. So we don't know exactly what that snap is, but folks who've analyzed the data suggest that in fact that might actually be electric discharge inside the dust devil. We know that dust grains can pick up a static charge the same way that you can pick up a static charge when you drag your feet in a carpet. And so it's thought that that snap is the actual discharge of a electric field on the rover microphone. So you have an idea. You want to study dust devils on Mars. Great. The next thing you need to do is find a grant program to propose to. As I said, there's a variety of grant programs. So what you're looking for is a grant program that supports that kind of research. This is perfect for what you want to do if you want to study Martian dust devils. This is the Mars Data Analysis Program hosted by NASA. It's a program which supports analysis of data that have already been collected by a Mars mission. So the Mars 2020 Perseverance data are archived online. Anybody can download those data. If you want to go look at that pop yourself, you can download this data and find that pop. This is the program you would apply to if you wanted to study data that are archived like that. about Mars. And so back in 2022, we put in a proposal to this program. Here's a description of the program's scope. The objective of the Mars Data Analysis Program is to enhance the scientific return from missions to Mars. And then it lists a variety of missions that have already been flown, and you can see they're listed Mars 2020 rover. So this is perfect. We'll put in a proposal to the MDAP program to study Martian dust devils. So how do you write a proposal to NASA? Well, you read the proposer's guidebook. So it's a very lengthy document that outlines all the requirements for a proposal like this. And this is one of the pages in the guidebook. These proposal solicitations come in the form of annual omnibus packages. In the case of NASA's space science research, it comes in the form of the Research Opportunities in Space and Earth Sciences, ROSES. ROSES comes out almost every year, and NASA, I guess as a joke, almost always publishes it on February 14th. So you can always say that NASA gave you roses for Valentine's Day. The book is quite lengthy and quite technical. I promise we won't go through it page by page. But it looks a little like this in the interior. So for example, if you want to write one of these proposals, you got to know the format that you're allowed to submit the proposal in. You can't just write an encyclopedia, 100, 200-page proposal and send it to NASA. Nobody would have time to read that. Okay, so NASA has some very strict requirements on how, for example, these proposals have to be formatted. So here at the bottom, for instance, you can see there's a length restriction, 15 pages. Now, 15 pages might seem like a lot, but when you're writing one of these proposals, 15 pages ends up being a really, really tight proposal. When I have students who are helping us with these proposals, they get very intimidated by the idea that they have to write 15 pages about science, but they certainly find themselves writing 20, 30, 35-page proposals, and then you have to pare it all down, so it's quite a challenge. Page size, 8.5 by 11. Font size, no more than 5.5 lines per vertical inch, so they're really down into the weeds. And why do they have to be that specific? Because if you're not, scientists are very smart and they'll find ways to cheat the system, and they do. Even with these kinds of details, they'll still find ways to cheat the system. So it's really, really particular. So what does one of these proposals look like? Well, again, I won't show you one page for page because they can be, 15 pages long. But here is the summary of the proposal that we submitted back in 2022 to NASA to fund this research. We propose to use the meta-meteorological data from the Mars 2020 lander to develop and test a model that predicts dust lifting by convective vortices, dust devils, on Mars. So this is the summary of that proposal. Different people have different approaches to these things. We tend to break our proposals down into individual tasks. But the basic rule of thumb with these kinds of things is these proposals tend to be 2 or 3 years long. So you're kind of thinking about it as 2 or 3 year-long projects. Recently, NASA began implementing what's called a dual anonymous review process. So you can see in the top left-hand corner where my name used to appear, now we just have anonymous. So when you submit one of these proposals, you have to write it anonymously so that the review panel that reviews it doesn't know who you are until right at the end. And the goal with that is to try to mitigate conflicts and biases that always arise when you have these kinds of review processes. It's been an interesting change. So for this proposal, we proposed to use data from that Meta instrument suite to analyze dust devil encounters, just like what I just showed you, and try to figure out how big was the dust devil, how fast was it moving, how much dust was it lifting. Essentially, do this. So this is a cartoon from our proposal, and here on the right-hand side, you can see as a panel, this is from an actual, for real dust devil encounter, like the one I just showed you. On the left, I'm showing you data from the Meta instrument suite. Don't worry too much about all the details. The basic picture is that green line shows you the wind get very windy during the encounter and then die back down. That's the dust devil encounter. And using these data, we can actually figure out how big the dust devil was, that's shown in that blue circle, and how fast the wind was blowing, how much dust was lifting. So this was the basic idea behind this proposal. How much dust are these dust devils lifting? So we write one of these 15-page proposals. Most of that page limit goes to the science, but of course some of it has to go to the budget. We got to pay for this. So what does the budget look like for a proposal like this? Well, I can't show you all the numbers here because some of these numbers are proprietary information for the university, but I'll show you the categories we look at. So you might not be able to read all of that, but these proposals fund a variety of different things here at the university. Primarily, they fund salaries. So they fund salary for myself. They fund salary for a GRA. That's a graduate student. So this proposal has money in it to support a graduate student to be involved in this research. A faculty member like myself, I'm on what's called a 9-month contract. So I'm only paid for the academic year. During the summer now, I don't actually get a paycheck. I don't actually get paid by the state. The state of Idaho does not pay me over the summer. So if I want pay over the summer, I need a research proposal like this to pay my salary. And so this is why there's summer funding in here for the PI, the principal investigator, that's me. So we have salaries, that's the biggest part. We have student costs. So if I've got a student working on this, we've got to pay their tuition for the program. So we include tuition. And then we include something that's called the facilities and administrative costs, F&A, or indirect costs. The university, of course, has to pay for the electricity, has to pay for the HVAC system. If we have a specialized lab, it has to pay for some of that specialized lab equipment. And a lot of the F&A built into the grant pays for those facilities. These grants also have an enormous number of federal auditing requirements that have to be satisfied, and so that requires staff. And so this F&A also pays for those staff. And so what happens essentially is we write a proposal with a budget, and then we tack onto that budget another 40% to pay for those facilities and administrative costs. And when you total up all the numbers, I don't know if you can read it at the bottom, this grant came out to about $180,000 per year for 2 years. So this grant is, what did I say, $360,000 for 2 years. Now that might seem like a lot of money, but remember that's salary, that's benefits, that's my health insurance, my graduate students' health insurance, tuition. So it does actually cost money to do this kind of research. That's actually a pretty slim proposal. Some proposals are $300,000 a year. So this is for 2 years. So you go through all this stuff, you write a science case, you write a budget, you put together one of these long spreadsheets, then you submit it to NASA, and you cross your fingers. Cross your fingers. These proposals go into NASA. Then NASA will convene a series of what they call ad hoc committees of experts to review these proposals and decide whether the science is good enough to spend $360,000 for 2 years on. The reviewers for these proposals are folks like myself who go to NASA and basically work almost for free to review these proposals. They give us it's a few $100s to review these proposals, but not very much. In 2024, for example, the Mars Data Analysis Program received 84 proposals to fund, 84 proposals, all of them more or less like that. And then scientists like myself will apply to review. Now, of course, I can't review my own proposal, right? If I propose to this program, I can't also serve as a reviewer. And so NASA will tap folks to serve as reviewers who have not submitted proposals to the program for that year. So these reviewers are other space scientists who have not submitted proposals to the program for that year. The reviewers are each sent about a dozen proposals to read through. Now, each of them, remember, is 15 pages long, a lot of technical information. It can take, hours and hours to read one of these proposals. And each proposal will usually get at least 3 reviewers. So 3 people will read each of those proposals. So there's a lot of overlap. And so we get a lot of kind of crosstalk between different reviewers to sort of check one another. Reviewers are scrutinized for conflicts of interest. So if I submit a proposal and my graduate advisor is one of the reviewers, he will not be allowed to review my proposal because we have a close relationship, and that would be considered a conflict of interest. If my wife submits a proposal, I would not be allowed to review her proposal because I would personally benefit from that proposal. So there are a series of conflicts of interest checks that NASA implements for each of these reviewers so that there are no obvious conflicts of interest. That oftentimes means that they have to find a lot of reviewers to avoid these conflicts of interest. Proposer readers are also sworn to secrecy. You can't share any information that you read in these proposals, and you can't use it in your own research. I could read one of these proposals and then just steal the idea in principle, but I sign an agreement to say that I will not do that when I agree to be one of these reviewers. Panelists will usually spend a few weeks after they receive these proposals reading the proposals on their own and then writing their own individual evaluations, which are submitted to NASA. And then NASA convenes the committee for about a week usually to review all these proposals and come together and decide on the grade for each of the proposals. What does a grade from NASA look like? You think that would be very stressful to get a grade from NASA, and it is. This is what a grade from NASA looks like. They don't use A, B, C, D, F. They use what's called adjectival rating system: excellent, very good, good, fair, and poor. I won't belabor all the technical details here, but the basic idea behind these different categories, an excellent proposal is a proposal that is compelling and has no flaws, no significant flaws. A poor proposal is a proposal that has some fatal flaw. So say, for instance, in my proposal for studying dust devils, I made an assertion that violated Newton's laws of motion. Well, that would be a fatal flaw, and I would get marked down as a poor proposal. And then the other adjectival ratings are somewhere in between. Good, most proposals sort of end up in the good category, but they can be a wide range. And then proposal reviewers are allowed to pick, halfway categories. So you can say this proposal was good, fair, or excellent, very good. So somewhere in between. When NASA selects proposals for funding, of course, they tend to choose proposals that are closer to the top of this chart. And so, for example, you can see in this bar graph here, the purple bars at the top, those are proposal categories, ratings that were selected. And you can see that a lot of the selected proposals are excellent, excellent, very good, maybe down to very good. The pink, these are proposals that were not selected. And you can see there were an enormous number of proposals in the good category. So that means a proposal is pretty good. Maybe it has some important flaws, but not like a fatal flaw. It didn't violate Newton's laws. I looked at this chart, and the first thing that struck me was somebody's proposal got a good, fair, and got selected anyway. You see that teeny tiny little purple line up the top right there? Somebody did a good, fair. I've never seen one of those happen before. I've been on a lot of these panels. A good, fair has never been selected. So I don't know. I'm really curious to know what proposal that was. So along with these adjectival ratings, you also get what's called a narrative to describe the evaluation. Why did the scientists decide that your proposal was excellent or was good fair? And again, I won't give you the details. These letters can be quite long, but this is what the evaluation for our MDAP proposal looked like. The proposed research would enhance our understanding of dust devils of Mars, which contribute to dust lifting and aerosol loading in the Martian atmosphere. And then it goes on to describe some of the technical details. It then cites a couple of things that they consider to be flaws. The proposal did not adequately demonstrate some index, so they had some concerns. But in the end, they gave us a very good rating. That was great. That was good news. In 2024, the Mars Data Analysis Program, as I said, had 84 proposals submitted. It selected 23 of those proposals. That's 27% selection rate that year. Between 2007 and 2024, the overall selection rate for NASA proposals to all the programs, Mars-focused programs, Pluto-focused programs, Venus, all those different programs, the overall selection rate was about 34. So 1 in 3 proposals is getting selected. So that means 2 out of 3 are not getting selected, right? 2 out of 3 are not getting selected. That's considered a very good selection rate. 30% is a good selection rate. So that means if you want to guarantee that you're going to get your proposal funded every year, you got to write at least 3 proposals. And as I told you, these proposals are a lot of work. They can take a month or more to write. Our proposal, fortunately, with this very good score, was selected for funding that year. So that was really exciting. You never expect to get funded, honestly. You never do. And whenever you do, it feels like winning the lottery. We got funded, and so we're actually working on this project right now. We're funded through next spring to conduct this research on Mars dust devils. But one of the things that's really great about these research grants is they're not contracts. The government didn't say, you have to study dust devils and we expect to see a report at the end of this that tells us how dust devils work. No, you say to NASA, here's an idea we'd like to explore, but there may be other things that come up along the way that we could also do with this funding. And so one project that came along as a result of this funding was this project, where we used the helicopter on Mars to estimate winds near the surface. That was not a project that we had planned, and we didn't even know we'd be able to do that project when we put this proposal in. But because we have a little flexibility about the research we could do, we were able to take this project on and actually just published a paper this year measuring winds for the first time using an aircraft on Mars. NASA's budget has fluctuated quite a bit over the decades since NASA originated. You can imagine, not surprisingly, maybe during the Apollo era, NASA got a lot of money. So upwards of $60 billion, and this is in present day dollars, not in 1960s dollars. And then since then, there was a significant decline. There was a little bit of a bump in the late 80s, and then the baseline for NASA funding has more or less flattened out over the last several years. That funding is separated into a variety of categories. Not everything that NASA funds is science. A lot of what NASA funds is space exploration. So here's exploration, development of aeronautical systems, space operations, space technology. There's facilities. You got to pay the people who work at NASA. Only about 30% of NASA's funding actually goes directly to science. Where does that money go? All over the United States. So here's a chart. You can't read the numbers down here, which this chart shows you how much NASA money goes to each state. So for example, California gets more than $1 billion a year. That's not surprising. There are several NASA labs in California, including the Jet Propulsion Labs, NASA Ames. Here in Idaho, there are a few $1 million in NASA funding to programs, Boise State, the University of Idaho, College of Idaho. You can see here in Idaho District 1, that includes the University of Idaho and the College of Idaho. There's almost $3 million of economic activity generated by this NASA funding that amounts to about $1 million a year. Sorry, no, more than that. Almost more than $8 million a year. Here in District 2, we have about $9 million in NASA funding at Boise State, and that generates something like $4.6 million of economic activity. So this is how NASA funding is used across the country. One of the programs that our NASA funding supports is the Telescopes for Teachers program. I'll let you watch that video yourself because I know I'm running a little long here. But that money, about $1 million, let us buy 50 robotic telescopes that we distributed around the state. So each of those dots is a teacher at a public school who got one of these robotic telescopes. And Rachel helped to train these teachers up to use these telescopes to actually do citizen science. These teachers could actually do astronomical observations with these telescopes. That's paid for by NASA. You may know that the proposed funding profile for NASA going forward is not as good as it has been in the past. This is what it looks like right now in the president's budget request in the next several years. There's a pretty significant decline in NASA funding. This is about a 24% reduction in overall NASA funding. It's worth pointing out it's a 24% reduction in NASA funding overall, but almost a 50% reduction in NASA science funding. So these are the different categories that NASA funds, and the orange bars show you the amount that's being cut from the proposed budget going into the next fiscal year. So about a 50% cut to NASA's funding going forward. As I've said, federal outlays for research and development are a small fraction of total outlays. You can see here is a plot showing federal outlays for research and development as a function of GDP, percent of GDP over the years. And it's kind of been on a steady decline. You can see there in that blue. Now we spend something like less than 1% of GDP on research and development and federal funding. It's worth pointing out that for every dollar that's spent on research by the federal government at the National Institutes of Health generates almost $3 of economic output. So this money is generating economic activity. It's not just money that's being put into a spaceship and then flown into space. It's actually staying here on Earth and making jobs for people. US research funding is on the decline. That is not true for other countries. If you look at Chinese research and development funding, they've been on a steady upswing for the last several years, and now they exceed US research funding by a fair amount, almost a factor of 2. More than a factor of 2 at this point. So other countries understand the benefits economically of research and development. This is something we probably need to do something about, at least from my perspective. Folks benefit from this in a lot of ways. I already talked about the economic benefits, but people benefit from this personally. This is Vera Rubin, back in her youth, conducting that research that led to the discovery of dark matter. Vera Rubin was a direct beneficiary of Vannevar Bush's vision that every boy and girl could achieve their highest potential. Her discovery of dark matter helped elucidate the history of the universe. Before the discovery of dark matter, we did not understand the dynamics of the universe, how it's expanding. And in fact, her discovery of dark matter led to the discovery of what's called dark energy, which was not expected at all. The universe, of course, as you probably know, is expanding, but the rate of expansion of the universe is actually accelerating. The universe is expanding faster now than it used to expand, and that's because of this mysterious dark energy. When you convert that dark energy into the equivalent mass, most of our universe is made out of dark energy. Only about 4% of the universe is actually made out of atoms that we're familiar with, everyday kinds of atoms like dogs and cats, trees, birds. Most of the universe is made out of these exotic materials. We do not know what they are. Dark matter, dark energy are a complete mystery. So how are we going to figure this out? How are we going to figure out what's going on? Observations from the Rubin Observatory are key for understanding what the universe is made of. These are the first pictures taken by the Rubin Observatory. They were just published a few weeks ago. Every dot in that image is a galaxy. Not a star, but a galaxy. Every dot. Everything that doesn't have a crosshair on it is a galaxy. The observatory will shed light on the mystery of dark matter. It collects an enormous amount of data every day. It collects about 20 terabytes of data every 24 hours. Just to give you a sense for that, what that would take over 3 years of watching Netflix, 10 years of Spotify to use 20 terabytes of data. Use that much data every day by taking pictures of the sky. That you just saw, that animation showed you 10 million galaxies in the sky. This is just a small piece of that image. Images like this are going to reveal this sort of profound mystery of the universe. We don't understand what most of the universe is made of. We don't understand what's driving the expansion of the universe. If this image represented the entire annual federal budget, that green square would be the entire 10-year budget to run the Rubin Observatory. Can you see it? That's the entire 10-year budget to run the Rubin Observatory. Okay, I'll show you again. This is the annual budget for the federal government. This is 10 years of funding for the Rubin Observatory. It's a really small star. U.S. investment has been a very small fraction of the federal budget, and probably always will be. And it doesn't have to be that much because it gives us these enormously profound insights into the universe, into the natural world around us. I don't know what we're going to do without it. Okay. And with that, I will stop and take any questions. Thank you very much. Yes, please. Oh yeah, when you like win the lottery a bunch of times over, yeah. Oh, it's a really great problem to have. Yeah, what you end up doing, you have to hire a bunch of students to do the work. I try very hard to focus on writing proposals that fund students, because for me, that's kind of one of the most important aspects of my job, is to support up-and-coming research scientists. So yeah, if you get lucky and hit the lottery multiple times, you just hire a bunch of students to do a lot of the work. Yeah, that's really great. It doesn't happen very often. Yeah, other questions? Yes.
How long did it take for the Rubin Observatory to come online?
Construction on the mirror started in 2007. I mean, planning has been decades. They've been planning that for decades. But actual, hardware began being constructed in 2007. So what is that, 18 years? Yeah. Yeah, first light. And we're going to see a lot of beautiful images like this over the next year. The data will be made public. I think they're going to be able to start archiving it publicly in about 2 years. As I've said, this instrument is going to generate so much data. It's created kind of its own new field of data science. They've had to figure out new ways to get data from Chile up to the United States for the data to be analyzed. So there's a whole group now, basically, whose job it is just to figure out how to manage those data. It's an enormous amount of data. It's going to revolutionize astronomy. Yeah. Other questions? Yeah.
I noticed on slide 63, it was like a bar graph of the funding. It said that like there's one that said STEM. I was wondering what, bar lights.
Yeah, right. This is the bar graph of the proposed funding profile for NASA going forward. You'll notice that the entire category called STEM is orange. That means it's zeroed out. That means it's gone. That is the education for students in STEM. The entire NASA science and technology education program will be gone if this request goes through. Those of you who might be familiar with Space Grant, Idaho Space Grant funds student research. That won't exist anymore. EBSCOR is kind of a separate pot of money. But yeah, there's certainly overlap between those different programs. That's right. That's right. Yeah. Other questions? Well, thanks so much for coming. I hope you enjoy your fireworks tonight and join us again in a month for the next talk.